AP Physics 2, 2019, question number 1. So I'm assuming you've read, excuse me, this question for the most part. This is a 10-point paragraph question. The main part will be the second part, which will be worth 5 points on the next page. On this page, part A, I, the first diagrams were 2 points, second diagrams were 2 points, and the I part at the bottom is worth 1 point. But bottom line is at the top here, I have something just to kind of get myself going. It tells you that the electric field in part A will be uniform and towards the bottom of this page. So I drew that. This is not great, it's optional, but just to kind of remind ourselves that the uniform field would be equally spaced uniform field lines pointing in the direction that the force would be exerted on a positive particle. In this case, we have a proton, and so the direction of force will be in the direction of the arrows. For an electron or negative particle of any kind, the direction of the force would be opposite that field. And it'll be a uniform force, causing uniform acceleration. But bottom line is this first diagram got 2 points. You got a point if you entered and had a curve towards the bottom. So it has to come in horizontally, curve towards the bottom. And it could just curve slightly and hit way over here and go out this right side, or anywhere along the bottom here, except for it cannot circle backwards because there's no force to the left, so the particle will never backtrack towards the left. It's basically like a marble rolling off a table or ball rolling off a table, which will come into play in part I at the bottom here. And this is a parabola. You didn't need to show it as a parabola, just as a curve that curved down and didn't backtrack. 2 points. And the second one, very similar. You could draw the same diagram and you still get 2 points. But this one can actually backtrack because the magnetic force is perpendicular to the motion at all time, according to the right-hand rule, as long as you didn't make it more than a semicircle. So this can curve, and it can come back through this left side as long as you didn't make it more than like I say, a half a circle. So it can intersect like I have here. It can look like the first diagram, or it could be another, very gradual circular path. Once again, it doesn't have to be perfectly circular, just curving down. All right, so 2 points there. Part 3, or I, is as long as you identify that the first answer, part I, is consistent with a uniform gravitational field, and then connecting the fact that uniform gravitational fields exert uniform constant forces in one direction, which is what the case is in part I. It's a uniform field producing a force, uniform force, with a constant force, constant acceleration in one direction, in this case towards the bottom of the page. And you can even talk about it being a parabolic shape. That might help a little bit, but probably wasn't necessary. So here's the paragraph part of this question. It's worth 5 points. And I've underlined a lot of the key phrases because when the people are grading these, that's what they're looking for, some of the key phrases. They read these kind of fast. And little diagrams can help you a little bit because one of the key factors here in this problem is that in this case, they've changed the direction of the electric field towards the top of the page. So now the electric force is towards the top, and the magnetic force is towards the bottom. And if they see this over here, they're pretty sure that you're going to be talking about the fact that those two forces can cancel one another. So, for example, here, my first statement, you don't have to literally put them, I put sentence number 1 here, sentence number 2 here, sentence number 3 here. That's good enough for a paragraph. And you're going to have anywhere from 3 to 6 sentences that are coherent, mixed in with maybe a little diagram that'll help you explain, or some little math at the bottom here I put in, which you really didn't need to put down there. But bottom line, the first thing is the electric field is towards the top on a positive charge, but it's still constant. So it'll be a constant upward force and cause the protons, it tries to cause the protons to curve upward. Conversely, the magnetic field is still down. It's going to try to cause the protons, like it did in the first part, to curve downward. So those are in opposite directions. Now, you should say something about the magnetic field being varying with the velocity. It's directly proportional. The magnetic force is directly proportional to the velocity. So therefore, number 4 here, the velocity can, and I don't like the way I said this. You maybe could have said the velocity can be greater than, equal to, or less than. Would have been a better way to say that, more professional. This would have worked, what I have here. But the electric force is constant. The magnetic force will vary proportional to the velocity in their opposite directions. So I've stated that. So, and then to make the connection that when the velocity is low, the electric force will be greater. Probably could have said the magnetic force will be low, would have been a better way to say it. And therefore, the particles will hit closer to location 1. And when the velocity is high, the magnetic force will be greater. That's the better way to say it. Connect the velocity to the magnetic force. And then, so then the downward force is greater than the upward force, will hit closer to location 3. And then kind of as a bonus, just to kind of show the person you really know what you're talking about, is that if the velocity is just right, the protons can travel straight horizontally and hit directly between 1 and 2. And I should show the math for that. So that they're not, if you show correct math, they're not going to take off for that, and it kind of helps them see that you're doing this right, you know what you're talking about. So I would include that little bit of math there. It shows that the velocity will be equal to the constant electric field divided by the constant magnetic field, and that would be the velocity that's, quote, just right to make a straight horizontal path.